Hey, did you understand the stuff about action potential and synapses in biology today?
Yeah, I did. Why?
Well, I didn't want to say it in front of the teacher, but I may have slept through most of it. Do you think you'd be able to explain it to me?
Yeah, for sure. I take it you'll want me to describe what neurons are too?
Yeah, if you don't mind.
Of course. So anyhow, a neuron is a specialized cell responsible for transmitting electrical impulses or messages around the body. They are the reason you feel cold when it snows, wet when it rains, and pain when your friend slaps you in the face. A neuron looks slightly different than a normal cell, however, and has some cool extra structural components as well. On one side of the neuron resides the dendrites. Dendrites are short, branched fibers that convert chemical information from neighboring neurons to electrical signals. More on that later. Then there is the soma. This section contains the body of the classic cell we all know and love. It houses the nucleus, mitochondria, and all other standard organelles enclosed by this phospholipid semi-permeable membrane. Then there is the axon, the largest and thinnest portion of a neuron. It consists of an elongated fiber that transmits electrical signals from the dendrite end of the cell to the other. This also happens to be the direction in which an action potential travels. Finally, there is the axon terminal. The axon terminal is where the electrical signals from the axon and dendrites are converted back to chemical signals for transmission to neighboring neurons.
Oh wow, that's pretty cool! So neurons are kind of like a telephone cable. They all connect together to send messages throughout the body?
Yes, exactly. When a neuron needs to be sent one of these messages, it fires, sending a signal across the cell and to other neighboring neurons.
How does that work exactly? Neurons firing?
Well, the process of a neuron firing revolves around the concept known as an action potential. An action potential is like a message being swiftly sent from one end of the neuron to the other via the axon. The scientific definition of an action potential is a rapid rise and subsequent fall in voltage or membrane potential across a cellular membrane, in this case, the neurons.
Okay, but how can a neuron just change the voltage around its membrane like that?
You remember ions from chemistry, right?
Yeah, they can be positive or negative depending on how many electrons they have.
And that's exactly how neurons do it. They transport positively charged ions across their membranes to create a steeper electrochemical gradient, or charge difference, between the inside and outside of the cell. The formal name for this charge difference is called the membrane potential.
Oh, that's so cool, but how do they do it?
Here, I'll show you. Here is a close-up of a portion of a neuron's axon. Notice how there are many sodium ions on the outside of the membrane and many potassium ions on the inside of the membrane. There's also a closed sodium channel on the left, a closed potassium channel in the middle, and an inactive sodium-potassium pump on the right. The sodium-potassium pump should be working right now, but I didn't have enough time to animate it.
No problem, I'll just imagine it.
Anyhow, you remember the concept of diffusion, right?
Yeah, it's when a substance moves from an area of high concentration to an area of low concentration.
Perfect. So what do you think will happen if the sodium channel were to suddenly open?
Some of the sodium from outside the cell would move to the inside?
Exactly. So anyway, here is a quick and dirty description of an action potential. I'll explain it qualitatively first, and then describe it again with some quantitative measurements after.
Sounds like a plan.
So remember that sodium-potassium pump that you're imagining doing its job right now?
Yeah, although how come it only has space for 3 ions on one side and only 2 on the other?
Oh, you're very observant. This is part of the whole reason why an action potential can happen. Because it removes 3 ions from the cell while only taking in 2, it will be constantly changing the voltage difference between the inside and the outside of the cell. The inside of the cell becomes more negative, and the outside of the cell becomes more positive. However, the spaces for the ions in the pump don't always have to be taken up. The pump can sometimes pump more net potassium than net sodium, or vice versa. Once the inside of the cell reaches a certain level of charge, the voltage-gated sodium channel will open. Because there are much more sodium ions on the outside versus the inside of the cell, diffusion will cause some of the sodium ions to rush into the cell. This results in the inside of the cell becoming much more positively charged, as there are now more ions in the inside than the outside. Once the inside of the cell reaches a certain level of positive charge, the sodium channel will close and the potassium channel will open. Because there are much more potassium ions on the inside of the cell versus the outside, potassium ions will diffuse out of the cell through the channel. This causes the inside of the cell to become more negative again, and the outside more positive. and once the inside of the cell reaches a certain level of negative charge, the potassium channel will close. Finally, the sodium-potassium pump returns the neuron back to its resting state, with more sodium on the outside and potassium on the inside. And would you look at that? The animation actually works this time. Note that one full cycle of the sodium-potassium pump uses up 1 molecule of ATP.
Wow, that's so cool!
It really is. Anyhow, here is a graph that quantitatively shows the change in membrane potential during an action potential. At the start, the charge is at its resting potential value, about negative 70 millivolts. Then, the charge slowly climbs up to the threshold potential at negative 55 millivolts. The climb up to negative 55 millivolts is generally caused by external stimuli, and sometimes the sodium-potassium pump too. Once the charge reaches this negative 55 millivolt threshold potential, the sodium channel opens and the action potential begins. It is worth mentioning that if the voltage does not climb to negative 55 millivolts, the action potential will not occur. During the action potential, the voltage climbs up to about positive 30 to 40 millivolts. This voltage climb is called depolarization. Once that voltage is reached, the sodium channel closes and the potassium channel opens, generally lowering the voltage to below the resting potential. This voltage drop is known as repolarization. Finally, the return back to the resting potential voltage is known as the refractory period. It's during this period when the sodium-potassium pump returns the sodium ions back outside the axon's membrane and the potassium ions back inside. The refractory period is also when the neuron can recover and prepare itself for another action potential.
Oh, that's amazing! Who would have thought that so much has to happen just for you to feel something?
I know, it's crazy. And this process is happening many times per second all across your body. Oh, one final thing. The action potential travels down the axon similar to a wave. The change in membrane potential happens in one part of the axon, which triggers it to happen in the section beside it, and so forth. It is also worth noting that this chain of action potentials across the axon can only happen from the dendrites to the axon terminal, and not in the opposite direction.
Okay, awesome. But what happens when the electrical signal from the action potentials gets to the end of the neuron? Aren't there gaps between neurons that would prevent the message from moving along?
Okay, yeah, there are those little gaps, but your neurons have a solution for that too.
Okay, yeah, I figured that much. I mean, I am talking to you right now, am I not? I more so meant, how does a message get across that gap?
Well, that process is pretty cool as well. It is often referred to as a synapse. Firstly, the little gap between the axon terminal of one neuron and the dendrites of another is commonly referred to as a synaptic cleft, and sometimes just a synapse as well. Because it is a physical gap, an electrical signal cannot travel across it. Instead, the electrical signal is converted to a chemical signal and sent across the cleft in the form of neurotransmitters.
Oh, that makes sense.
So, to send a chemical signal across the synaptic cleft, an electrical signal must first arrive. And you guessed it, that electrical signal arrives in the form of an action potential. Once the action potential arrives at the axon terminal, it causes the voltage-gated calcium channels to open. Remember that an action potential is a rapid change in voltage across a membrane. Because there are more calcium ions on the outside of the neuron versus the inside, some of the calcium ion diffuses into the cell. The calcium ions then bind to vesicles carrying neurotransmitters, the chemical counterparts of the electrical signal and message. The binding of the calcium ions cause the vesicle to move towards the edge of the axon terminal to a docking protein. Once the vesicle approaches the plasma membrane of the axon terminal, it binds to the docking protein and begins releasing neurotransmitters into the synaptic cleft via exocytosis. After the neurotransmitters are released, they travel across the synapse to receptors and ligand-gated ion channels on the adjacent neuron's dendrites. Once the neurotransmitters reach the receptors and the ligand-gated ion channels, they bind to each other. Depending on the type of neurotransmitter, this may cause the ion channels to either open or close. If the neurotransmitter is excitatory, it will cause the ion channels to open, triggering an action potential down the neuron. However, if the neurotransmitter is inhibitory, it will cause the ion channels to close, preventing another action potential from occurring. And that's the process of a synapse.
Awesome! Thanks so much for helping me out with this. I understand action potentials and synapses pretty well now.
No problem. Always happy to help. Though next time, you should maybe just record the class instead, because I don't always pay attention to everything.
You know, that's probably not the worst idea. Anyhow, I'm getting kinda hungry now, so I'm gonna go grab some lunch. Thanks again, and have a good afternoon!